right. Hello and welcome to the next episode of 3D30. Today we're going to do something a little different. This is Ask Me Anything. So today we're going to have a metal, additive manufacturing and 3D printing question and answer session. It's going to be a little strange, so stick with us. So in case you're new to 3D30, 3D30 is Velo3D's LinkedIn Live and YouTube Live channel. We host this about every 2 weeks, but with the trade show schedule, obviously Formnext is coming up. That would be pretty close. We're going to do one on Formnext, so stay tuned for that in a couple weeks. But make sure you follow Velo3D to get the latest schedule, because we kind of change these all the time. We're pretty fluid about our schedule, and we schedule these without much lead time. So there's not really a calendar. You have to follow us to find out what's going on. So over the last few months, we have been active at trade shows. We had IMTS not too long ago. And we've had conferences that we're attending and speaking at. We have had our own roadshow series, which is a great session where we deep dive into Velo3D technology. And during those sessions, we get asked a lot of great questions. And for today, inspired by those sessions, we want to hear from you to get your great questions. We're going to kick it off, though, by going through some of our top questions. And then what we really want to do, though, is hear from you, understand what you're curious about when it comes to metal 3D printing, or specifically, are there some secrets that you'd like to know about Velo3D technology? I'm not going to be the one answering those questions, though. So to help us get to the bottom of this, we brought on one of the magicians of Velo3D technology, Matt Karesh. Let me bring you onto the show. All right, there's Matt. He is our technical business development manager, and he's going to help us answer all these questions. So keep in mind, this is a live show. We want to hear from you. What we have seen, though, is that there is a slight delay between when we broadcast and when you see the broadcast. So when you submit a question, we might not see it right away. So make sure to get your questions in early so that we have enough time to get to them. And we'll pay attention to those and answer them as we go. So Matt, we've had you on the show not too long ago, so I want to ask about your background, but what's new?
Yeah, thanks for having me and the opportunity here to interact with some of our customers. For me, you mentioned roadshows and trade shows. So I was at TRX last week, which is a event hosted by America Makes, to bring a lot of the industry experts together and share a bunch of knowledge. So listen to a lot of great presentations from folks like Ursa Major, Aerojet Rocketdyne, NASA, some folks in the Army. Caught up with a lot of those different people and talked about a lot of the different things that are going on in the industry and some of the challenges people are facing. So it was a really good time. I made a lot of good connections and hopefully get some good collaboration coming out of it.
So when you're at a show like this, I know that there's a mixture of new people that you've never met before and also established contacts. But let's say you meet somebody for the first time. What is the first thing that you tell them about Velo3D?
Yeah, so it's a little bit of, poking around and figuring out what context makes the most sense. If you're talking to an engineer or a manufacturing person or more of a business person, but really try to help them understand what Velo is all about and why we are different. So trying to bring a production additive solution to the market so people can actually use the technology and in the way that it's been marketed for the last 10, 15 years, right? Of this almost Jetsons approach of you put it in, hit the button, and it comes out all done. And we all are very aware that is not how the technology works, but that's the ideal goal to work to that whatever direction or CAD you put into the machine, you get this beautiful part coming out. So give them a flavor of some of the geometry things we can do, but really from my perspective and my experience in the additive industry, try to highlight some of the more supply chain centric pieces that we bring to the table.
And so I assume they come in with some idea of what Velo3D is. So I kind of want to ask two questions here. It's like, what's the most common thing that they already know about Velo3D? And then the second question is what's the thing that they get wrong about Velo3D?
Yeah, and those are sometimes intertwined. Yeah. Support free comes up a lot. That's a term we used to use quite a bit. And we're gravitating away from that. It's not that our capabilities have changed. In fact, they've gotten better, right? But we want to make sure we're giving a very clear message that you can't print any geometry that you can dream up without supports. There's a place and time for when support for you makes sense and when it doesn't. And that can be from a design perspective or from a cost and throughput perspective. So there's that piece. And then one of the big ones that is still lingering out there a little bit about Velo is the closed loop control, and Velo being this black box of all these secret parameters, and you put something in and the machine is this, AI machine learning platform, and it's watching everything that's going on in the powder bed and changing things on the fly all the time. Absolutely not the case. That we went down that route early on in our roadmap, and quickly found that there's some pretty strong resistance to that level of technology in the industry, especially in regulated industries like aviation and medical and things like that, where you need fixed processes to be able to control the outcome. So we are very much not using closed loop control today. Our process parameters are fixed and tend to be very open with our customers about exactly what we're doing and how we're able to achieve the things that we are achieving.
Yeah, I've heard somebody say you don't want to play a game of Plinko every time you make a metal part for an airplane. So it's just that randomness or that on the fly type of control. We do have a question though, and we're off to a good start. I like to see the early questions. What is the minimum wall thickness that Velo3D can print in? And I'll say in aluminum, but I would like to break this out. He's talking about ALSI 10. So if you can talk about that a little bit.
Yeah, so we don't have ALSI 10 today, but not that different from F357, which is the aluminum we are printing in today. And aluminums behave slightly different than the other alloys that we're generally working with, your nickel-based or titanium alloys. But to get to the question, the material thickness or the wall thickness that you can achieve is directly related to the angle of the surface that you're printing. So your best case scenario is going to be a straight up and down vertical wall, and that's where you're going to be able to achieve your absolute minimum thickness. So in aluminum, on the order of 350 microns as a leak tight wall is a safe number. And when we say leak tight, we're not saying it's going to hold 1,000 psi. It simply does not have through wall connected porosity where you'd have a fluid get from one side to the other. Then there's another scenario of what is the minimum existing geometry you can create, right? And so you're not as concerned about being leak tight, but for things like heat exchanger fins where thermal conductivity is important and minimal cross-sectional area. So in that scenario, we can get down to roughly half of what we can in the leak tight. So think 150, 175-ish microns thick. And again, that's in a vertical wall orientation. So as that wall starts to come over an angle, that thickness is going to go up. And that's just directly related to the stability of a weld pool. And at lower angles, especially on the super low angles, to keep a stable melt pool, you're generally using a larger weld bead. So that inherently results in a thicker wall.
I think I got a picture of one of our parts that we've printed in aluminum right here.
Perfect.
Kind of see those thin features next to some context there with the hand holding it.
Yep, and I did forget to mention Scalmalloy as well. We do have some parameters for Scalmalloy in addition to F357.
Nice, great question. All right, off to a good start. So one of the questions that we actually have for the audience now that we've got some folks kind of joining us is, what is your level of additive manufacturing background? Let's say on a scale of 1 to 5, or let's just keep this text-based. You could just freeform, but we'd love to hear from you. How much experience have you had in AM, and what is your background? Obviously, we're going to wait for the delay, but we'll take a look at that as that rolls in. So Matt, you kind of mentioned some of the differentiators. What is the big thing that you want to communicate in terms of productivity? I think you mentioned was a big differentiator for Velo3D. How do we achieve a higher level of productivity than other solutions on the market?
Yeah, I think it depends on how you look at productivity. And so one of the big ways to look at it is scalability in my mind. And so it's how repeatable, how reliable, how scalable is your solution? And are you creating parts on this one-off snowflake machine that's the only machine that can generate these components, or you're creating something that's on I'll call it a cookie cutter, where you can repeat that result over and over. So the way we've approached the additive technology is that our system and our software and our technology solution is designed to be very repeatable, going from machine to machine, vendor to vendor. And that allows you to do all of your development work and trials and testing and dialing in on a single machine serial number, and then very rapidly, with or without purchasing additional machines, scale your solution. So we've got a network of contract manufacturers that have Sapphire printers, Sapphire XCs, running various different alloys. So let's say you have an Inconel 718 printer in-house, you're developing parts on that, but you don't necessarily have the capacity to go into production. And your company, for whatever reason, doesn't want to do a complete vertical integration. So you can take that development build file, that print file that you validated internally, and then send that out to the entire contract manufacturing network. Those systems out in the network will run off of that exact same print file. So they'll run the exact same laser commands that were run on your machine to give you the exact same result back out. So that's a fairly unique value that we bring. And we marry that with a lot of metrology that we've built into the system that allows us to do things like automated calibrations, where we're calibrating as often as once every single build, and really helps us dial in the machine, the hardware, to be in as optimal state, as healthy of a state as possible before printing. And by doing that very easy and very often, you're then keeping your hardware in a very reliable, again, state that allows you to reproduce those results that you did on machine 1, 2, 3, whatever it may be.
Okay, and I do want to kind of dive into the calibration thing a little bit, but real quick, Mark, I see your comment here. You say you can't see anything. Are you referring to the video in general, or the reply to our question for the audience about what your experience is? If you want to reply to the question, you could just freeform text like you sent in the question there, and that's fine. We're just kind of trying to get an idea of what people's experience is. So on the machine calibration side, now I have been aware of some other solutions where it's a very manual process, and there's some time involved and some expertise involved and some, let's say, variation in results. What does Velo do to sort of resolve some of that?
Yeah, so to kind of set the baseline, right? If you go look at, I think one of the specs is coming out of NASA Marshall, where they address recommendations for calibration of an additive machine. And I forget the exact terminology, but it's, our recommendation is to calibrate once every 3 to 6 months. And that is recognized as being due to the challenges and productivity of the ability to calibrate those machines. So what they're trying to say in a nice way is you should calibrate these machines way more often, but we know it's really hard to do. Therefore, here's a concession. What we're able to do is, because we have this metrology built in the system, we've come up with some novel ways to calibrate things like our optical path and our powder bed and our gas flow. We've got this set of automated routines where you come into the machine, you click a few buttons, the machine goes into a routine on its own and goes and checks the different things. There's 5 major calibrations that the machine runs through. Depending on how many you're doing, you're on the order of, anywhere from 1 to 2, 3 hours to get through the entire routine, which in the context of, let's say you're doing a 100-hour, 150-hour build, right? That's a really small investment to make sure that your machine is in the best possible state before you kick off that build.
And you mentioned kind of a lot of equipment on board for this calibration. I assume some of that helps you during the process too. Can you talk a little bit about the in-process monitoring?
Absolutely. So like you said, we use a lot of the same sensors and metrology that's in the machine to not only calibrate, but watch the process throughout the duration of the build. So we're looking at things like laser alignment and the powder bed health. So actually dimensionally characterizing the deviations in the powder bed, not only from the spreading of the powder, but from protrusions of the melted metal that we're getting, which is a natural phenomenon to happen when you're melting powder with a laser at high temperature and then it's cooling off into forming. So we take all of this information during every single build and we pull it into this quality system that we call Assure. And so number one, what does it do? It just stores and documents all this data, right? So that you as a user have the ability to go back and access that data if for whatever reason in the future you need to. It's there. The other thing that it's doing is distilling all that information down into a very simple and readable format where you can very quickly understand how healthy the process was. And if something did go wrong, very quickly drill into what the root cause for that issue was. Was it you had an oxygen excursion where something had a leak and we had oxygen enter the system? Or did we have some sort of interruption? Maybe the argon in the facility went down and the machine threw an error, so the machine paused. What Assure will do is it'll tell you exactly what happened for that interruption, not only when it happened, but how long it occurred for, what layer it occurred on, and give you all of the reasons why the machine threw an error and stopped. So it's not just a kind of like, I'll say marketing thing of, hey, we have process monitoring. It's a functional tool that tells you how good the process was during your build, and it's also a diagnostic tool to go figure out what happened if something does inevitably go wrong.
And can you just recover these builds, or do you, like you mentioned, there's an interrupt? Is that it? Is the part gone, or what happens then?
Yeah, no, that's a great question. So, this is something that happens throughout the additive industry, right? Builds pause for a number of reasons. And it's going to depend on the level of criticality of your components and getting into the nitty gritty of like the stresses and the function of the specific zone that the build has paused in. So let's say you're in a fairly benign region, or let's go super extreme here. You're just in like the extruded stock support structure region of the part, right? Don't care at all about the material properties of that section of the component. Absolutely, you go through a restart procedure, make sure that you get a good, clean restart, and we have ways to do that, and then you continue on. There will inherently be sections of your component that are just not tolerable to restarts, and it's really good to understand that up front so you don't waste time on the manufacturing side trying to restart or trying to figure out if you're allowed to restart. So that's predefined. If the build pauses, you kill it and you start over. But you also know, if you can restart it, that within a certain time frame, go follow the procedure, recover it, and keep going. So yeah, it's a little bit of a depends, but for sure there's opportunity there.
Nice. And you mentioned before, so you're monitoring lasers, you're monitoring, I think you said powder bed health, and it sounds like there's something going on around the environment. I can't think of if I were to pick 3 things that are critical to get this process to work properly. It's like, well, what are your lasers doing? What's the powder doing? And then what's the atmosphere doing? It's got to go a long way to checking off the boxes in terms of getting quality out of this thing.
For sure. Yeah. So looking at things like oxygen content and dew point and humidity humidity and making sure we actually ran into an issue where humidity was too low on our systems, which did some funky things with powder. So it's important to understand like the exact status of all those things for what is generally a very sensitive process.
Nice. We have another question on how do you handle multi-laser machines? I mean, all of our machines are multi-laser. They at least have 2, or in the Sapphire XC case, 8. So how do we handle the multi-laser capability of the machines? And is stitching between these lasers, do we stitch, I guess is what he's asking.
No, that's an excellent question. And yeah, like Mike mentioned, all of our machines are multi-laser, which is should be an immediate, I don't want to say red flag, but you should question it for every machine in the additive industry, right? It is, how do you handle that stitched region? So Velo has a pretty robust solution to that. And I've hinted at some of them already, but we do the laser position calibration before the build, or at least once a week. That's what Velo recommends. And that calibration by itself is looking at 500 points across the build plate for every single laser. And that's basically defining the baseline of your Galvo lookup table. That's telling you, when I say laser go here and you actually went here, you adjust the Galvo table so that those come together, and then that's like, you're good. You've zeroed it out. That's great to start a build off that everything's zeroed, but we're all aware that environment changes, especially when you're looking at putting 8 1 kilowatt energy sources into a powder bed. You're going to have energy into that system. Therefore, the thermal environment of that system is going to increase. Temperature is going to increase. And because these optics are very sensitive to temperature changes, we know that they're going to drift. So there's kind of 2 ways to approach it. You take this like OCD approach to isolating the optics from a thermal perspective, which in some cases we do. They're not open to environment or anything like that. But more proactive than that, we actively monitor the position of the lasers throughout the build. So every single layer, we're looking at where the lasers are firing relative to where we're telling them to fire. And if we see those start to deviate out of what we think is, or what we define as intolerance, we actually go adjust the tables and bring them back into alignment. So that is the only piece of information or input in our system that is changing during the print. And it's simply making sure that the lasers are staying within the original calibrated spec of their position that they're supposed to be in. So if you ever have a chance to see any Velo3D parts in person, almost all of them are stitched. And we'll always challenge people to try and find the stitched region of the components. It is next to impossible to be able to find that because our laser alignment is so robust.
I've got one of those here. So this is a nice part. This was made with 8 lasers on the Sapphire XC, and kind of to your point, I know it's just a photo, but yeah, really clean surface finish on this. And this is as printed. You can still see it welded to the build plate and powder seeping out through the relief holes there. So no post-processing on this one, but it just kind of gives you an idea. And for scale, one of our favorite pictures, one of my favorite pictures. So nice. So we do have another question coming in. Yeah, flip it back to us here. So changing materials, do we have any features that ease the process to swap materials?
Interesting question. And I think I have a little bit of a spin of an answer that maybe you weren't expecting. But so yes, changing materials is not ideal, and our systems were absolutely not designed to change material. That goes back to our kind of fundamental philosophy of designing this technology to be a production solution. And in a production scenario, you don't want to be changing major things like the feedstock of the system. So again, when you set up that system, you ideally have it with material X, whatever that is, in mind, and you're running with that material. You have the ability to change materials on our systems, but like we said, it's not a straightforward, easy process. It's involved, and it was never designed or intended to swap materials on a daily basis. The way we approach that is, if you are interested in printing in something other than what is in your system in-house, so you've got Inconel in-house and you want to print in titanium, right? We have this really strong network of contract manufacturers who have these dedicated systems in these other alloys that you can turn to, in a drop of a hat, and get them running on a system that is dedicated. There is no concern for contamination, or do I need to, how deep do I need to clean this machine to make sure that every speck of powder got out before I put my new alloy in? How much time am I going to spend worrying about that? And am I going to always have this question mark in my mind of all the components going forward that there's some level of contamination? There are certain industries that straight up say you cannot change material on these machines because of the risk of contamination. So why risk it? Just leverage existing infrastructure, if you will, of the contract manufacturing network and get those components that you need until you're to a point where you have enough demand that it makes sense to bring on another system dedicated into that other alloy. So hopefully that makes sense.
Yeah, no, it really clears. I think the risk about going to these, if it's bad for one industry, you got to assume that there's a reason, right? So even if your industry doesn't require you to specialize a machine on a certain powder, it kind of makes you wonder why this industry would do that. They've probably had some experiences in the past where that became a concern, I would assume.
For sure.
Yeah. So I do want to ask a little bit. You mentioned some parts protruding from the powder bed, and I kind of wanted to double back on that. What's happening to make the parts protrude? What is going on there?
Yeah, it's fairly simple when you get down to the basic phenomena that's happening. You're melting metal powder with a heat source, in our case a laser, obviously beyond the melting point, and then when it solidifies and cools down, it's naturally shrinking. So as that metal is forming and shrinking, it's deforming, right? It's not going to stay in place and shrink. So depending on the shape of that geometry and the amount that it wants to shrink and deform, it's at times tending to want to form and peel up out of the powder bed and protrude, what we call protrude, which is a general challenge for the additive industry because of the way the next layer of powder is typically spread on these systems. And so generally the way that's done is what's called a fixed recoat blade. And that's either a solid metal blade, so think of like a snow plow, or a soft blade. So think of things like a comb, a fine comb, or some sort of flexible material, right? And all those blades are doing, they're on a fixed Z height, a fixed track, and they push powder from one side to the next. And they are defining the next 50 micron, 30 micron, 80 micron layer that you are going to build, physically defining it with the bottom of that blade. What allows us to get away with building these really challenging geometries that are naturally tending to protrude is in piece our non-contact recoater. And what that's allowing us to do is it's a 3-step recoat process where we kind of rain down powder from above, and we're putting down an order of magnitude more powder than we need for our final 50 micron layer. We're using a normalizing blade, so you can think of that as your traditional fixed blade recoater. But again, that's an order of magnitude higher than where our final build plane is going to end up. And then for the third and final step, using a vacuum system to get down to the final 50 microns. So we're giving ourselves, again, an order of magnitude of tolerance to any metal protruding up out of the powder bed. And anything more than that, you're concerned about part quality, right? So it's good to have that level of tolerance, But it's also good to know when your part is heading in that direction, because something may inherently be wrong, and you may want to go back and fix your design. So it gives us this kind of competitive advantage that allows us to print really low angle surfaces that tend to protrude, but also allows us to print really fragile structures, like those very thin walls and high aspect ratio components that will, on other systems, typically interact with that fixed blade recoder and either cause damage to the recoder or flick and fling powder or distort the geometry and cause for poor part quality.
Well, we're kind of over the 30 minutes here. I think we probably got about halfway through our questions, but thank you for the folks online who asked questions. That was it's always great to hear your insight. I'm more interested to get your questions in front of Matt than my questions. But Matt, do you have any final thoughts on like some of the big topics you've been talking about, or what's coming down the pipeline? What's exciting you right now?
For me personally, it's material characterization. So, we give everyone the ability to generate these awesome features they can scale with our technology. The next major step in my mind is getting the design allowables, the material curves in the designer's hand way up front, so that they can appropriately design their components for the technology and have a really good understanding of what to expect out of the material, rather than building and testing and then getting that information back. So I think for Velo, you're going to see a strong push here in the next few months to try and democratize some of that information and go characterize that for the greater good of our customers and the industry, and really try and further the adoption of the technology.
Yeah, I think the material side, if I were to put it in a layman's terms, it's kind of like what the rest of the industry does, what subtractive manufacturing does. They basically buy a cake and cut it into shape. We're baking a cake in the process. Like, we're actually taking flour and eggs, and this is how you actually make the material itself. And I think that's lost on folks, where they don't realize that the process is actually going, and it's much more like baking than carving, where you're with this process creating your material properties. And I think that that gets lost on some folks, but it's a great thing to highlight. And it looks like we've crossed the spam filter. We're starting to get crazy comments. So good time to wrap it up. Thanks for joining, everyone. And Matt, thanks for your insights as always. And stay tuned. Maybe we'll have Matt on for another session here in the future.
Yeah, maybe to sign off, we'll also be at Form Next. I'll be there. Sounds like some of you will be there as well. So come find us, and we'll be happy to continue the discussions.
Awesome. Have a great weekend, everybody.